Of all 160 or so planets and moons in the solar system, Mars has so far received the most interest from astrobiologists. There are many signs that show that very early in its history, Mars was much like Earth, with large areas of liquid water, a thick atmosphere, ample sources of energy for life, and a good inventory of organic molecules.
In fact, what I like to say when I compare the two planets is that you don't have to invent words to describe Mars. You have mountains, you have canyons, you have polar caps, you have dunes.
There is evidence that Mars had a warmer and wetter past. Dried up riverbeds, vast canyons blasted out by epic floods, valleys carved by raging rivers, polar ice caps, volcanoes, and minerals that form in the presence of water have all been found.
There's a lot of evidence for liquid water earlier in the planet's history, much earlier, about 4 billion years ago, and perhaps some transient water in the time since 4 billion years ago.
But the evidence indicates that all that water disappeared from the surface billions of years ago as Mars cooled down and lost its atmosphere. Did life ever get a foothold on the planet?
As we're looking for evidence for ancient life on Mars, some people think that actually we already had some evidence of that life landing on our own planet. And the best example of that is the Allen Hill meteorites.
We had a piece of Mars here in the lab. We still have it. Allen Hills 84001, a rock that was chipped off Mars by an impact millions of years ago, wound around in space, landed on the Earth in the Antarctic ice sheets, and during the 1984 spring collection season, as that ice was melting and those black rocks were picked up in the melt pools, we realized by the gases that are included in that piece of rock that that's a piece of Mars. And we took it apart at microscopic scales. And we had a big scientific controversy because there were scientists that were claiming features in that rock could only have been produced by biology, and other scientists saying, nope, you can get that with geology.
The search for life on the Red Planet started decades ago. In 1976, a search for microbial life on the Red Planet was performed for the first time ever. 2 decades later, in 1997, the Pathfinder mission took a new step forward in this search for life adventure. It found magnesium, aluminum, iron, and phosphate in Martian rocks, which are all possible life-supporting materials. In 2008, the Phoenix spacecraft explored Mars' North Pole. After digging a few inches, it found a white material that evaporated several days later. The analysis of that material revealed it was water ice. Satellites scanned both polar caps and found that there was a lot of water ice under a layer of frozen carbon dioxide. If all that ice ever melted, a more than 80 feet deep ocean would cover the whole planet. The same satellites also discovered that there was ice buried everywhere beneath the desert plains. That was a shocking discovery. Mars had huge amounts of water ice everywhere. But could life exist in the buried ice itself? We now know that there are extremophile microorganisms able to live in similar environments in the dry valleys in the Antarctic, here on Earth.
Currently, Mars is very dry and very cold. It's like some regions in Antarctica today, and it's kind of like a very cold desert. So liquid water would not be stable. If you opened up a container of water, it would immediately evaporate because it's so dry.
Buried ice was found under a layer of dry dirt, as happens on Mars. At the point where the dirt met the ice, there was a thin film of liquid water where extremophiles thrived, just for a short time. These microorganisms remain frozen and dormant most of the year, and they only flourish for a few warm weeks during the summer.
Today, Marcus could still live at depth, at some depth, favored by the presence of thin films of water or maybe more liquid water, because the deeper you go, the more the chance that water could be liquid.
During the Martian summer, it's common to reach 20 degrees Celsius at the equator, so the buried ice might melt and create similar conditions to those found in the Antarctic dry valleys.
Any microbes that might have been there, they're probably living within the rocks or under rock coatings. So that's one of the analog sites that my group's been investigating, is microbes that are living underneath the surface, because that might be viable for Mars as well.
A future mission could eventually prove whether this hypothesis is true or not. But there is another possibility, that liquid subsurface water exists on Mars. Mars' huge volcanoes, such as Olympus Mons, could contribute internal heat to sustain subsurface water. This would imply that hydrothermal vents could exist on Mars as well, and therefore it might be also possible that extremophiles, similar to the ones that thrive in the terrestrial hydrothermal vents, might also exist on Mars. However, this is quite unlikely. Everything would change if we were able to find liquid water on the surface. On September 2015, NASA's Mars Reconnaissance Orbiter made an incredible discovery. This spacecraft provided the strongest evidence yet that liquid water flows intermittently on present-day Mars.
It's not pure transparent water. It's very briny water, very salty water, which allows it to remain stable for a little while at the surface, because the pressure at the surface of Mars is very, very small.
Using an imaging spectrometer, researchers detected signatures of hydrated minerals on slopes where mysterious streaks were seen on the red planet. They darken and appear to flow down steep slopes during warm seasons, and then fade in cooler seasons. This finding proved what anyone could have imagined. On Mars' present-day surface, there is liquid water. Maybe in some of those ephemeral streams of liquid water, microbial life has managed to arise. We will have to wait for future rovers and explorers to confirm this hypothesis. What will really change our understanding of the Red Planet are the NASA and ECA missions, both part of the Mars exploration program. Since 2007, the main goal of space missions to Mars was not just to follow the water, whether in the form of ice or liquid water, but to explore its habitability, and above all, to seek signs of life.
The more we investigate Mars, we obtain more clues that the ancient history of Mars was certainly supportive of life. And then that final step of, did life actually evolve? And then if it did, where did it evolve? And what clues are remaining today? Because that was so long ago.
The ultimate aim of missions to Mars is to prepare for human exploration, a step that would really be a new milestone for mankind. The first step in this ambitious exploration program is the ExoMars program, a partnership between ESA and Russia's Federal Space Agency, Roscosmos, with the participation of NASA. Its primary scientific goal will be to search for possible biosignatures on Mars, past or present. ExoMars is a multi-spacecraft program. The first ExoMars mission, ExoMars 2016, is called the Trace Gas Orbiter, TGO. The goal of this orbiter is to study the Martian atmosphere for the presence of methane and other gases, gases that might be linked to some biological processes. The second mission in the ExoMars program is the 2018 ExoMars rover and landing platform. The ExoMars rover is a rover with a 2 meters core drill to sample various depths beneath the surface where liquid water may be found.
The drill was supposed to penetrate the first couple of meters within the sediments. This way is more probable maybe finding evidence of viable salts.
The third step of this enthralling Mars exploration program is the NASA mission, Mars 2020. The aim of the Mars 2020 rover is to study diverse rocks and soils to understand past habitable conditions on Mars and to seek signs of ancient microbial life. One of its functions is to monitor weather and dust in the Martian atmosphere and test the ability to extract oxygen from the red planet's carbon dioxide atmosphere to prepare for future human exploration. Any of these breakthrough missions might solve the enigma of whether there is past or present evidence of life on Mars.